Hello, everybody, and welcome to another talk in the Astro 3D ECR Astronomers in Australia seminar series. My name is Dr. Amelia Fraser-McKelvey. I'm a postdoc at the University of Western Australia, which is part of ICRAR, and my co-chair today is Dr. Dorota Bayer, who was at Swinburne University of Technology. So before we begin today, it's important for us to acknowledge the traditional custodians of the land on which we meet today. So the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build today. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. So myself and our second speaker today are speaking to you from the land of the Whadjuk Noongar people. My co-chair Dorota is joining us from the land of the Wurundjeri people of the Kulin Nation. And our first speaker today, Simon Murphy, is speaking to you from the land of the Gadigal people of the Eora Nation. We pay our respects to their elders past and present and extend that respect to all First Peoples joining us here today. So why are we here? This series is facilitated by Astro 3D, which is the ARC Centre of Excellence for All Sky Astrophysics in 3 dimensions. It's a bit of a mouthful. COVID-19 has affected our ability to travel and present at international seminars this year, especially for us in Australia. The time zones mean that often meetings that take place at 2 or 3 a.m. in the morning pass. This lack of opportunity to network could disadvantage junior astronomers when entering the job market. This series aims to combat these issues by providing a platform for junior Australian astronomers to present their work to the world. So thank you, world, for coming. A little bit of housekeeping. We've got 2 talks over this hour. The first, each will be 20 minutes in length with 5 minutes for question time. Please save your questions until the end of the talk, and you can feel free to either pop them in the chat function, which Dorota will read out, or you can raise your hand and ask it yourself. These talks are being recorded and they're going to be placed afterwards on the Astro 3D YouTube channel for educational purposes only. So by being here today, you're agreeing to abide by Astro 3D's meeting code of conduct. Our second speaker is Aditya Manuwal, who is a PhD student at ICRAR at the University of Western Australia. Aditya is going to be talking to us about unresolved H1 lines in the Eagle simulations. So Aditya, you can go ahead and share your screen and take it away.
Yep, sure. Okay, is that good?
Perfect.
Okay, so hi everyone, I'm Aditya, and today I'll be talking to you about the work that I've been doing as part of my PhD here. And it's focused on the asymmetries of H1 lines of Eagle galaxies. So what we're trying to do is we're trying to address the origins of these asymmetries. So first of all, let's understand what is an H1 line profile. So it's known that every neutral hydrogen atom produces a emission of 21 centimeter wavelength when it goes from a parallel spin state between photon and the electron to an anti-parallel state. Now, this is useful because you can observe the cold ISM of galaxies using this emission. So H1 line profile in particular is basically the representation of this flux that comes from the neutral hydrogen in the cold ISM in the space of line of sight velocity. So on the y-axis, you have the flux, and on the x-axis, you have the line of sight velocity of the gas. So for example, you're seeing here on the left an SGSS footprint of a galaxy from xGASS, and on the right, you have the corresponding H1 line profile. And we're concerned with the asymmetries in these kind of profiles, essentially. So why H1 is itself interesting is because it extends out further out than stars, So that means that it can trace the heliodynamics better than any other tracer, which means that if the helium of those 2 galaxies are interacting in some way, it's better traced if you see in H1 other than any optical counterpart. So that's the utility of H1 itself. Line asymmetries in particular are interesting because theoretically you expect local instabilities to cause some asymmetries, but they should wash out in 1 or 2 rotational periods. But if you go to observational samples and you measure the asymmetries of observed line profiles, what you find is that most of the galaxies are actually asymmetric in their H1 line profiles, which means that there are some physical processes contributing to the asymmetries and which are causing high incidence of asymmetries when you observe them. And it's important to study why that is the case. So what we do is we use the Eagle simulations to do that. And we do that because it simulates both dark matter and gas particles self-consistently. So you have all the physics that you require, like cooling of gas, star formation, stellar feedback, gas enrichment because of supernovae, and also black hole physics. everything you need in a realistic universe. And it uses Planck cosmology to evolve the universe from about redshift of 20 to redshift of 0. So it's useful to use these simulations because you can actually use the physics of the dark matter halos as well as the galaxies and understand how they relate to each other and contribute to the H1 line asymmetries. So the problem with Eagle, though, is that it is not resolved enough to resolve your cold phase. So you have to do some post-processing to get your H1 masses in your gas particles. So what we do is we use the Ramath-et-al prescription, which is shown on the left here. It uses the UV background, temperature, and density of the particles to get the total neutral hydrogen in your gas particles. And then you further partition this into the atomic component, the atomic hydrogen, using the Blitzer-Nosarowski prescription, which converts the total mass into the H1 mass using the mid-plane gas pressure of the gas particles. And once you do that, you actually have the H1 mass in all the particles. So you can assume each particle to be a Gaussian in the line of sight velocity space. So it's like a Gaussian profile. And then you can sum of such profiles for all the particles in your galaxy. And then you can convert that mass profile into the H1 line profile using the formulation shown here, which depends on the distance. And you also have an additional noise term, which is used to emulate the instrumental noise in your instrument. So that's how you get the H1 line profile, essentially. When you partition in this way, in Eagle, you find that the H1 fraction, H1 to gas mass ratio, is actually having a bimodal distribution. So either you have very H1 poor gas particles, or you have very H1 rich particles above 0.5. So it means that if you want to get a reasonable line profile for a particular galaxy, you should sample enough H1 rich particles. So we find from our test that we need at least 1,000 such particles to do that. And that's what we use as a cut when we select our galaxies, essentially, apart from the stellar mass cut of 10.9 solar masses. Then when you do that, you have a H1 profile like this. It's a noiseless H1 profile for the galaxy shown on the left, which is the H1 surface density map. So once you have these profiles, now you need to measure the asymmetries. So what you do is you start with a velocity, a central velocity. We use the flux-weighted velocity. That's what we use. And then you divide the profile into two sides using this velocity. So what you do is you integrate on both sides of this velocity till it reaches 95% of the flux on that particular side. So that's used to get your profile edges. So you do that on the lower side and the higher side, you have the edges now. And then you can do away with your central velocity. And you define a systemic velocity based on the positions of these edges, which is the midpoint of these two edges, which is similar to what people do in observations, essentially. So now this is the region that you'll use to define your asymmetries. And there are different ways to do that. So we use 3 different measures because they measure different types of asymmetries. So top left, you see the lopsidedness, which is basically the offset between the integrated flux on both sides, normalized with the total flux in the whole profile. In the middle, you see the velocity offset, which is the offset between the systemic velocity and the velocity where the flux is equal on both sides. So ideally, they should be coincident, and they should be 0. So you can use this as a measure as well. And you normalize that with the total width of your profile. And then in the third, you have the normalized residual, which is basically what you do is you have the systemic velocity. You take the velocity bins equidistant from that velocity, and you measure the offset in the flux on those 2 bins. And then you add up these offsets throughout your profile. And then you normalize that combined offset with the total flux in your profile. So just because of the way they're constructed, lopsidedness measures the more global scale asymmetries, and normalized residual measures more finer asymmetries in your profile. And we find that they're all well correlated with each other. So we combine them into a single combined asymmetry, which we're calling ACOMB, which is shown here. And we're using that to study the asymmetries essentially. So before we move on to explore the origins, we actually want to see if the asymmetries from Eagle are reasonable or not. So we compare them with observations. In this case, we're using the xGASS sample. So what we do is in xGASS, you have 3 different parameters which are important when you infer the asymmetries of profiles. First one is velocity resolution. Second one is the instrumental noise, and third one is the distance to the galaxy that you zoom. So velocity resolution is basically the amount of smoothing that is there in the profile, which affects your signal to noise, and therefore also affects your asymmetry. As shown in the bottom left, you have 3 different profiles with the 25th percentile, median, and 75th percentile in xGASS, while the other 2 parameters are fixed to the median value. The distance and noise are fixed. And you see that the asymmetry does change as your resolution becomes poorer or delta V increases, but doesn't change too much. And signal to noise also reduces. If you look into a similar plot, but for noise, you see that in the middle panel, the asymmetry changes by about a factor of 5, from 0.04 to 0.19. And signal to noise changes as well. So noise has more a role to play in terms of the asymmetries, as you expect. And on the bottom right, you see a similar plot for distance, which also causes a change, but it's not as drastic as noise, but it's more drastic than change in resolution. So all this is suggesting that you need to take these factors into account when you compare with observations. So what we do is we use the modal values of these parameters for Eagle, and we generate the echelon line profiles. And then we compare to xGASS. But the problem with xGASS is the xGASS statistics is lower than the Eagle. So to take care of that, what we do is we divide the H1 stellar mass plane into a grid, and then you sample the same number of galaxies from Eagle as you have in xGASS. And then what you do is you compare those realizations that you have made of Eagle with the xGASS galaxies above 10.9.2 of H1 mass, because you don't have Eagle galaxies below that, just because of the cut that people have used. So we do this basically 100 times. So you have 100 realizations of xGASS-like samples from Eagle, and then you compare them with the xGASS. So here you are seeing the results here. So on the solid blue curve is basically the realizations from Eagle, and the scatter in that curve is basically shown in the shaded region, which is the interquartile range in those realizations. The solid blue curve is the xGASS centrals above 10.9.2 in their H1 mass. And the dashed curves are basically all the Eagle centrals and all the xGASS centrals. So you see that if you focus on the solid curves, you can see that they're quite consistent overall. The asymmetries are consistent, which means, okay, good, we can go on to explore the origins now. So first thing we look at is basically the difference between satellites and centrals. And we also define asymmetries in two kind of ways. So one is the asymmetry based on a random line of sight from towards the galaxy. And other one is the maximal asymmetry. So as you go towards more edge-on view of a galaxy, you see more and more velocity structure in its line profile. So you capture more asymmetries in the velocity structure of the galaxy. And as you go towards more face-on case, for a spiral galaxy, you see more Gaussian kind of profile. So you're not seeing the velocity structure anymore. So you have to have some sort of inclination to actually capture that. So what we do is we orient the galaxies edge-on, and then we rotate them in 5 degrees about the vertical axis, and we select the maximum asymmetry amongst those asymmetries. And we call that as the maximal asymmetry of the satellite, of the galaxy. And that's what you see here in the pink curve. The blue curve is for the random angles. And the dashed and solid curves correspond to the satellites and centrals respectively. So the first thing you'll notice is that the maximum asymmetries are quite high compared to the blue curve. There's a significant offset, which means that galaxies are more asymmetric than you actually see them observationally. The second thing you'll notice is that satellites are systematically more asymmetric than centrals, which is telling you something about the environment they live in. Satellites are exposed to more stripping processes, and that's what you're seeing here. So the next step is what are the processes which are contributing to the asymmetries in satellites? So we look at 3 different types of processes. So ramp pressure stripping because of the IgM around the satellites, the tidal stripping because of the central halo, and the interaction between satellites with other satellites, basically. So these are shown in 3 different panels here. So on the y-axis, you have the asymmetries. Blue are the random asymmetries, and the pink is the maximal asymmetry. And on the x-axis, you have on the bottom left, you have the ramp pressure, which is the ratio of the ramp pressure with the gravitational pressure. In the middle panel, you have the ratio of the H1 radius of the galaxy with the tidal radius. And on the bottom right, you have the ratio of the interaction energy because of the collision based on the relative velocity of the satellite with other satellites, divided by the total internal energy of the satellite. So increase in any of these parameters means increase in that type of stripping force, essentially. And you do see that the ramp pressure and tidal stripping are quite correlated with their asymmetries, especially the ramp pressure. And if you look at the points here, they correspond to the halo mass above 10 per 13. So the correlation actually increases as they move to higher halo masses, which is what you expect and which has been suggested in literature as well. So that we are getting an idea, okay, ramp pressure and tidal stripping are actually contributing to the asymmetries of satellites significantly. You also look at assembly history of your halos. How do they relate to the asymmetries of your galaxies? So we look at central specifically here to avoid complications related to the environment. You have on the bottom left, you have the formation time of your halo. on x-axis, which is the time where 50% of your halo mass was assembled. In the middle panel, you have the substructure mass fraction, which is the amount of fraction of the total halo mass which is in the substructures. And on the bottom right, you have the offset between dark matter center of mass and the potential center of the halo. So the first, in the first panel, you'll see, okay, there's an anti-correlation between the asymmetries and the formation time, which means that if the halo was formed recently, it is more asymmetric. It is having more asymmetric galaxies inside it. Okay, more asymmetric centrals. And because more recently assembled halos also tend to be having more unrelaxed state, more substructure, you see a positive correlation with the substructure mass fraction and the offset here. It is telling you, okay, the assembly history is actually affecting your asymmetries also. And this also means that if you look at a given mass, you should see more asymmetry as you go back in time. That's what you see on the top panel here. As you go to higher redshifts back in time, you see more and more asymmetries. And in the bottom right panel, you see that for a given redshift, for a given time frame, you see that as you look at higher halo masses, you're getting more and more asymmetric galaxies inside them, which is also telling you about the hierarchical nature of assembly, right? So it's clear that assembly history is actually related to your asymmetries. And we also see at look at feedback. So on the y-axis, you have the combined asymmetry, maximal asymmetry, and the x-axis, you have the fraction of gas mass which was heated. And you see positive correlation. Okay, the feedback in last 30 mega years is related to your asymmetries. And you also see that in the distribution. So cyan is the total sample and blue is the heated sample. So if you compare the two, if you look at the, this is the covariance matrix, which you're using Spearman rank coefficients. So I want you to focus on the first column here. So on the top one, you have all the centrals, and on the bottom one, you have only heated centrals. So if you look at the, look at the top one, you see that, okay, substructure mass fraction and fraction of gas mass heated are having similar correlation coefficients, which means, okay, the environment and the heating, because of the feedback, is contributing similarly. But if you look at the bottom panel, where you're only seeing the heated ones, you see that the correlation with the gas mass heated has actually increased, but the substructure fraction is not having any correlation, actually, if you look at the p-values of this correlation. So if there has been a recent heating, the environment plays a smaller role, and the heating is dominating our asymmetries, essentially. We also look at the rotational support in the galaxies versus asymmetry. So on the x-axis, you have both bottom right and bottom left x-axis are measuring your rotational support in the galaxy. And you see that there is an anti-correlation, clear anti-correlation. So your higher rotational support means more symmetric H1 line profile, essentially. But if you have a lower rotational support, you can have a diversity in your H1 line asymmetry. That's what it's showing you. So if you have a rotation supported system, it will produce an H1 line profile, which is also symmetric, statistically speaking. So I'll leave you with the summary of my results. So asymmetries in Eagle are consistent with observations, which is a good thing. In general, galaxies are far more asymmetric than they appear. Satellites are more asymmetric than centrals, which is basically because of ram pressure and tidal stripping. H1 line asymmetry is a good indicator of halo assembly history and therefore dynamical state. The feedback dominates over environment in cases which underwent a recent event, and a highly rotationally supported system produces a symmetric H1 line profile. And that's all I had to say. Thank you.
Thank you very much, Aditya. Great talk. Now I'll hand over to Dorota for questions.
Thank you, Aditya, for the nice talk. Do we have any questions from the audience? Yes, Luca, please.
I can start asking one, Aditya. Thanks a lot. On your last point about the kinematics, yes. When you were talking about rotational support, is this the rotational support of the H1 or of the general galaxy with other traces?
So this is only looking at the rotational support in H1.
So does this mean that in Eagle you have galaxies where the H1 is not rotationally supported?
Yes, you do have them, yeah.
How do you explain them physically? Because that's called gas. If it's stable, that should be rotating.
I understand what you're saying, but the thing is that in Eagle you have a lot of clumpy galaxies as well, and partially I think it's because of the physics, the way they have assembled, and partially it's because of the resolution limit of Eagle. So it's both factors combined, I think.
Oh, okay, interesting. Thank you.
Yeah.
We have a question from Hamza.
Hi, thanks for the nice summary. I had a question about, like you do this for one simulation set, I guess, Eagle. How general is it? Does it work for other ones? Have you tried? And I mean, probably that would give us some indication of the physics of that's going into these processes, right?
Yeah. So you mean using different kinds of simulations, or?
Yeah, illustrious, or I mean, various other kinds of simulations, different kinds of.
Oh, right. Okay. So we did look at asymmetries in illustrious actually, because we have some people working on illustrious in ICRAR itself. And there is a colleague of mine called Adam Watts, and he had published a paper recently about asymmetries in illustrious. So they also find similar results actually, as we do. And we had compared our asymmetries with illustrious as well. So they are similar. There's some offset between the two, but they are similar overall. The differences are not too drastic. So I think in terms of the physics, the thing is that both of them are implemented during different codes, and different schemes. So there is some difference because of that. But I think overall the main results are similar in both simulations, at least illustrious and Eagle.
Yeah, that's nice to know. Thanks.
Yeah.
So let's thank Aditya again, and both of our speakers actually, both Simon and Aditya, for 2 fantastic talks today. Thank you very much also to the audience for listening.